Okay, so let's get going on today's class. So today we're going to continue our look at chapter 4. Last time we introduced the idea of probabilities and distributions and using the normal curve table. Today we're going to delve a little bit deeper into the normal curve, some of its properties, and one of the reasons why it is so widely used and so widely occurs, especially in psychology. But before we get to that, just one last announcement for today's event presented by the IUSB Psychology Club, Comic Books and Psychology. So this is going to be happening in about 3 hours today in the cafeteria next to the grill. Free food and drinks, no need to RSVP at this point, just drop on by. And I'll be covering this new and exciting field of analyzing comic books to discover things about how we behave, how we think, basically to do research in psychology. So come check it out, and maybe it'll give you some ideas for a future advanced lab, perhaps. But on to chapter 4. So as we were mentioning, we are getting very, very, very close to being able to do inferential statistics. We're getting very close to the point where we're going to be able to take actual psychology data, actual results, and do the same kind of analyses that professional psychologists do. So we're almost there. We can almost do the ninja stuff. We just need a little bit more fundamentals, and that's what chapter 4 is all about. We're just finalizing our skills so that we can get to that point. And I always find it helpful to keep in mind, now we're getting close to the end goal, what, again, the importance of all of this is. So I'll return to this example over and over again because it is a very dramatic example. So again, if you are working as a psychologist, you will never, ever, ever in your life study a population. It's almost impossible unless you have a population of people who are so unique. There's only like 4 of them around in the earth. You will still probably not have access to all 4 of them, right? So populations are very, very impossible to study. What we can study, though, is samples. So what we do is we take a sample, we try things out on it, we treat that sample, we try different approaches, different treatments, different types of interventions, and we can measure what happens to that sample. So we don't need inferential statistics to know what happens to the sample. So if we're trying a new approach with autistic children and we develop this new interactive educational approach, we can measure those 14 autistic students and we'll know whether or not they improved. We'll know whether or not they got better. All we need is descriptive statistics, means and variances to help make sense of the data. What we don't have, though, is the ability to generalize. And without the ability to generalize, science is at worst useless, right? You just won't be able to ever do anything with science because it can't go beyond the lab. Or without the ability to generalize, science would be at best elitist, and it would be reserved for those individuals who can pay the millions of dollars to psychologists or to other scientists to run the studies on members of their own family, on people that they wanted to be able to pay those high prices for. Thankfully, though, we have inferential statistics, which means that we can run these 14 individuals, know that our intervention worked for them, and then intelligently generalize that to every other person in that population. So every other autistic child on the face of the earth, without having to test them individually, we can generalize our results from our sample to that population. So that, again, is the end goal. That's what I want you to keep in mind. That's why statistics is so vitally important for a science like psychology, because otherwise it just wouldn't be very useful, or it would be useful, but only for a very select few. All right, so today we're going to revisit the normal curve, the normal distribution. And as we saw last time, this curve often happens when a number of different things need to occur. A number of different factors determine your score on a particular measure. So in this case, this is the visual example that we saw last time. Each of these balls that is being dropped out of this one area up here Each of those balls, its position in the lower portion of this device is going to be determined by how many times it hits a pole and goes left, and how many times it hits a pole and goes right. There's approximately 9 different rows of poles, and in each place, the ball can either go left or it can go right. And the normal curve occurs because its final position will be the accumulated lefts and rights that it goes through in its 9-pole journey. And most of these are going to have some combination of lefts and rights and end up in the middle, but some of them are going to have extreme combinations of all lefts or all rights, and they're going to end up on one of the extreme edges. Well, the same is true for individuals, and as we're going to see today, the same is also true for samples. So this is a kind of spoiler alert in terms of why the normal distribution is so important, because so many of the things that we study in psychology through the use of samples ensures that we're using a normal distribution. All right, so on that note, we're going to talk about samples and populations. We're going to talk about a very important concept called the distribution of sample means. I'm going to warn you right off the bat, this is a kind of multi-layered inception type situation that we're going to go into, so be prepared for that. We're going to talk about the central limit theorem, which is what I like to call the mathemagic behind the statistics that we do. All right, so first off, samples and populations. So as I mentioned before, samples is what you have access to. You don't have access to the population. You're never going to test the millions, maybe billions of people that you want to know something about, but you do have access to samples. You do have access to 50, 100, 1,000 people. You can test and measure those samples. And what we do is we take those samples and we use them to estimate these population parameters. So one of the most straightforward examples is if you find the mean of a population, the mean of a sample, you can infer the mean of a population. If you want to know how tall the average male is, for example, what you can do is you can just randomly take a sample of 1,000 males, measure their height, and say, I'm going to estimate that that's what the population mean is, whatever my sample mean is. So that's what we do. We use samples to estimate these population parameters. However, there is a challenge inherent in that procedure. So if you're dealing with a population, if you're dealing with that population there and it has some sort of distribution, maybe you don't know what the mean is, and maybe you don't know what the standard deviation is, right? So we're dealing with a population, maybe it's a new population, one that hasn't been researched before, and we don't know what the mean of that population is. We don't know what the standard deviation of the population is. What can we do to find out? Well, we can start taking individuals from that population and measuring them, right? We can start taking a sample. So let's say that we grab that individual from the population and that individual from the population, and we grab that person up there and that individual right there, and we get that individual right there. Let's say that that's our sample. Our sample is going to give us a sample distribution. And that sample distribution, we know what the mean of that sample distribution is, because we can just measure these 5 individuals and calculate their mean. We know what the standard deviation of that sample distribution is, because we can just measure these individuals and calculate the standard deviation. So we want to use this information to estimate this information. The challenge is that sometimes we're in this situation here, where the sample that we have gives us, for example, a mean that correctly estimates the population mean. But remember that we know nothing about this population. So we don't know if the 5 people that we chose came from this particular section of the population, or if the 5 people that we chose came from over here, and here, and here, and this individual here, and this individual here. So that's another 5 individuals. But when we calculate the mean for this sample, we're going to get a very different sample mean. And in this case, we're going to very greatly underestimate the sample mean, the population mean in this instance. And it even gets worse, because not only do we not know if it maybe came from this extreme side of the population, We also have to contend with the fact that maybe it came from this extreme side of the population as well. So we don't know where our sample came from because we don't know the population that we're dealing with. So to kind of find out about the population, we take a sample, but we don't know where that sample came from because we don't know what the population is like. So, excuse me, the problem here is that different samples from the same population, like these two samples from the identical population, they're going to have different sample means. And in reality, most sample means are not going to equal the population mean. Just by chance, most of them are not going to be the same as the population mean. They might be off by a little, they might be off by a lot, but most of them are not going to be the same, and that's known as sampling error. So the sampling error is just the amount of error, or the deviation, between a sample statistic and its corresponding population parameter. So it's a deviation between, in this case, the sample mean and the population mean. So that's an issue, and that's a challenge. And what we need to kind of figure out is how can we tell what is the probability of selecting a sample with a specific characteristics from a population. So we need to kind of figure out what is the probability of getting a sample like this versus getting a sample like this. In other words, what is the probability of getting a particular sample? Now, we can tell kind of intuitively that one of these is highly likely to occur, and the other one is completely unlikely to occur. All right, so just to kind of give you an example, let's say that you and a friend of yours signed up for a IQ Olympics, right? So you're signing up for this competition. It's going to be an IQ Olympics, and you are going to be randomly paired with people in the population for your team, right? It's going to be a 6-person team. It's going to be you and random people paired with you from the population. So you go in there, and your first person, let's say that this is your sample from the population, your first person that you paired with is some elementary school student. And you're like, all right, you know, kind of on the low end, that's fine. Next person, high school dropout. And you're like, okay, you know, sure, they're out there. Next person, let's say high school student. Next person, college student. Next person, college graduate, right? And you take a look at your sample, and you're like thinking to yourself, I could have done better. I could have done worse, but I'm not kind of surprised, right? I got a couple of lower picks. I got a couple of higher picks, but, you know, I'm not surprised. I'm kind of not astonished. Nothing seems out of the ordinary here. This seems kind of believable. Your friend takes a look at their team, and the first person on their team is a college graduate. And you're like, all right, that's kind of, you know, good for you. Second person on their team is a professor at a university. And you're like, oh, man, really? All right, you kind of got lucky. You're starting to feel that they got lucky. Third person, Bill Nye the Science Guy. And you're like, oh, my goodness. Next person, Neil deGrasse Tyson. You're like, no way. Last person, Elon Musk walks through the room. He's like, yep, randomly on your team. And you're all laughing because you all know the chances of that are so small. It's insignificant that they would randomly just happen to pick 5 of the smartest people on the planet to be part of their team. So we kind of know, we kind of intuitively understand that a sample that looks like this, that comes from the center of the distribution, is much more likely to occur than a sample that looks like this, that comes from the end of the distribution. So we want to kind of figure out what is the probability of getting one of these weird samples, one of these extreme samples, or what's the probability of getting one of these more regular, normal, from the middle samples. And if you recall, when we think of probability, we want to think of a proportion. When we think of a proportion, we want to think of a proportion of a distribution. So if you want to know what is the probability of picking Elon Musk out of the population of the world, what you need to do is you need to take the distribution of the population of individuals, and you can figure out the probability of getting one individual from that world. So the probability of picking these individuals, or in our case, the probability of picking an individual that smart or smarter, we can get that from the unit normal distribution curve. We looked at that last time using the tables. However, we're not interested in the probability of getting an individual. We're interested in the probability of getting a sample. So because if you're looking for the probability of an individual, you look at a distribution of individuals. If we want to know the probability of getting a sample, we have to look at a distribution of samples. So this is where it gets kind of inception-y, because we're going to go from a distribution of individuals, take out a sample, and then go to a distribution of samples, aka the distribution of sample means. So, distribution of sample means, what do? It is kind of hard to wrap your mind around it, but it is a collection of sample means for all possible random samples of a particular size. So how big is your sample? Is it a 10-person sample? Is it a 5-person sample? In this case, it was a 5-person sample. Every possible mean from, every mean from every possible random sample that can be obtained from a population. So what we mean is that if you had a population of individuals, let's say we had a population of Earth, and we were looking for the mean IQ for our sample, right? We want to find out the mean IQ for our sample. To find the distribution of sample means, what we would do is we would take out samples of 5, right? Let's say that that was the size of the sample that we wanted. We would take a sample of 5 people. We would measure their IQ. We would take the average. Let's say that the first one had an average of 106. Back into the population they go. We take out another possible sample. So this would be sample 1. We then take out sample 2, measure their IQs. Let's say they get 112. Put them back in. We can take out sample 3, measure their IQs. Let's say they got 95. We then take sample 4, measure their IQs, take the average. Let's say that they, right on the average, they're 101. We then do this for sample 1,583,437,281. And they have an IQ of 109. All right? We're not even close to done. But this is what I'm talking about in terms of the distribution of sample means. It's a whole bunch of sample means, right? From taking a whole bunch of samples. And then what you do is you take all of these raw scores, and much like we did before, you take those raw scores and you make yourself a distribution. And this is the distribution of sample means that is going to tell us how unlikely it is to get Elon Musk, Neil deGrasse Tyson, and Bill Nye the Science Guy on the same team versus getting somebody, a selection of individuals with more normal IQs on the same team. So that's what it is. It's a little bit difficult to visualize when you're thinking about such huge numbers. So one of the ways that I like to kind of break this down is to think of dice rolls. So we'll simplify it a little bit. Let's just look at the population of dice rolls. And if you look at the history, the population, every single dice roll ever done with fair dice that were 6-sided, you would find that the average for that population was 3.5. And that's because the average points on a dice are 3.5. You go 1 plus 2 plus 3 plus 4 plus 5 plus 6, divided by 6, you get 3.5. If you looked at the distribution of all the dice rolls in the history of the world that were done with fair dice, that would be the frequency distribution. All right, because fair dice means that each outcome, 1, 2, 3, 4, 5, or 6, are all equally likely. That's what this frequency distribution is telling us. So let's say that we started taking samples from this population, aka let's say that we started rolling dice. And we started with a single dice, just one dice roll. And for each sample that we took, we measured the mean of that sample. So we changed now from IQ to dice rolls. So we go from IQ to dice rolls. And when we roll a 5, we take a look at that and we say we have one score in our sample, it's a 5. 5 divided by 1 is 5, so the mean of this sample is 5. It's a little bit of a simplified one. We roll it again, it's a 6. The mean of that sample is a 6. We roll it again, it's a 1. The mean of that sample is a 1. We roll it again, it's a 3. The mean of that sample is a 3. If we went all the way to every possible single sample that can be taken from those, we would actually only need 6. That's every single possible single sample because there's only 6 sides. We actually don't even need this guy anymore. All right. So we get every single possible sample from that population. The sample means are going to be 3.5 because the sample means in this case are going to be the 5 plus the 6 plus the 1 plus the 3 plus the 2 plus the 4. That's all of them. Add those all up, divide by 6, you get 3.5. So in this case, if we plotted the distribution then of sample means, we have all the sample means, and we plot the distribution, it's going to look just like the population distribution. And this is the only time that happens. The only time your distribution of sample means looks like your population distribution is when your sample size is 1. And that's because your distribution of sample means is a group of individuals, which is your population distribution. So that's important to realize that the only time that the population distribution is going to look like the distribution of sample means is when that sample size is 1. And as you know, psychologists don't use sample sizes of 1. We like to have as many people in our samples as possible. And the reason is because of what happens to this distribution of sample means as your sample size increases. So what does happen? Well, let's take a look at a sample of 2 dice rolls. So for 2 dice rolls, you roll 2 dice, you see the scores, add them up, figure out the mean. So you add them up, you divide by 2. So we got 2 dice now being rolled instead of 1 dice. If we found all possible samples from this population and we took each of theirs, so once again, we're rolling the dice and we're seeing what happens. And on that first roll, we get 2 3s, so the average is 3. On that second roll, we get a 1 and a 6, so the average is 3.5. On that next roll, we get a 5 and a 4, so the average is 4.5, right? And we keep doing this until we get all possible samples from that population. What we're going to find is if we took the mean of all of these sample means, the mean of those sample means would be 3.5. So notice that the mean of the sample means is always the same as the population mean. That's a good thing. But what happens to our distribution of sample means? Well, this time it changes shape. The distribution of sample means changes shape. And in this case, that's the distribution of sample means. So we saw this as the distribution of outcomes for a roll of 2 dice, because there's only one way to roll an average of 1. You got to roll a 1 and a 1. There's 2 ways to roll an average of 1.5. You either roll a 1 and a 2 or a 2 and a 1. So this is the distribution of sample means. That is the population distribution. That's the shape of the distribution of sample means. Notice it's changed shape once you go to a sample size of 2 or more. Excuse me. So we can continue to play this game, and we'll add another subject, right, to our sample. We'll increase our sample size to 3 dice rolls now. So you're taking 3 dice and you're rolling them. And once again, for every single possible combination of these 3 dice, you add up their scores, you divide by 3, you find the mean for the sample for these 3 dice rolls. And what we would find again is that if you took the mean, the average of those sample means, you would end up with a mean of 3.5. But importantly right now, well, once again, you can see that the mean of the sample means is the same as the mean of the population. But importantly, that distribution of sample means changes its shape again. And it turns into that distribution of sample means. And if we continue to play this game, we'll increase the size of our sample to 4 dice. Once again, roll the 4 dice, take the average, add up the scores, divide by 4. We will find out that if we take a mean of all the sample means, we'll get a mean of 3.5. And once again, the distribution of sample means changes, and that's the distribution of sample means. And then finally, let's finish it off with a sample of 5 dice rolls. We have still a distribution of sample means average of 3.5, and now that's the shape of our distribution of sample means. So notice an interesting thing has happened to our distribution of sample means. It has changed shape, but it hasn't changed shape into some random kind of arbitrary shape. It's changed shape and it's starting to look very much like a normal curve. And we're going to see that there's a good reason why this occurs, why sampling distributions, this is also known as sampling distribution, often become these normal curves. All right, any questions so far? All right, so that's great when you're rolling dice and you can roll them hundreds of times or use Excel to kind of figure out all the different combinations. But you really can't do this in the real world, right? I have never been able to run 10 subjects in an experiment and then say, okay, thank you very much. Let me run another 10. Okay, thank you very much. Let me run every combination of 10 subjects. You can't do that. So we need to know a distribution of sample means, but we usually only have the one sample. We're usually only working from that one sample of 10, 20, 30, 50, 100 people, however many it is that we have. We only got the one sample. So how do we figure out this distribution of sample means? How do we figure out this this distribution that we need to know where our sample is from the population? Well, for that, we turn to the promised mathemagic of the central limit theorem. So the central limit theorem is a very important idea. It's what makes statistics possible in terms of inferential statistics. And it's the idea that for the theorem, it's not just an idea, it's a theorem, it's a proof, that for any population that has a mean and a standard deviation, which is basically every population, right? Every population is going to have a mean and a standard deviation. For any population with a mean and a standard deviation, the distribution of sample means from a sample of a certain size, right? From a certain sample size, will have a mean the same as the mean of the population and a standard deviation that is related to the standard deviation of the population and equals the standard deviation divided by the square root of the size of the sample. Don't worry about why it's a square root, it just is. And importantly, and thankfully, it will approach a normal distribution as n approaches infinity. So this is what makes psychology possible. Any population, this will work for. It doesn't matter what that population is. And you can figure out what your distribution of sample means from that population will be. You know the mean that it'll have, you know the standard deviation that it'll have, and importantly, you know the shape that it will have, and it will approach a normal distribution as your size of your sample gets bigger and bigger and bigger. So that is why we spent that time using the normal distribution table. That is why that normal distribution table is the first table in your appendix. That's why we spent the time figuring out what score do you need to be in the top 10%. While we went through the examples of starting with a raw score and finding a percent, starting with a percent and finding a raw score. The reason for that is because all of our sample distributions, all of our distribution of sample means are going to be normal curves. And that's why when we're asking ourselves, is this a really weird sample or is this a sample from the center of our population, we can figure it out by comparing our sample to that normal distribution curve, to that normal distribution table. All right, so let's take another kind of visual of this. So if we have a population distribution, remember that the central limit theorem said that for any population, and what that means is any shaped population, a population with any distribution of scores, as the size of the sample increases, your distribution of sample means is going to get closer and closer to a normal curve. So if this is the population distribution over here, and this is the distribution of sample means, that's the distribution of sample means for a sample size of 1. And as we recall, this is the only time that your distribution of sample means is going to be the same as the population distribution, because this is a collection of individuals, this is a collection of individuals. But as soon as we go to a sample size of 2, the distribution of sample means changes its shape. Sample size of 3, sample size of 4, sample size of 5. And we can see that with this population distribution over here, once we get to a sample size of 5, we're already looking at a pretty normally distributed distribution of sample means. So the distribution of sample means, again, becomes a normal distribution because a number of different independent factors, i.e. independent people, are contributing to the score in that particular sample. So the chances of getting extreme scores goes down because you need 5 extreme individuals in order to get extreme scores. The chances of middle scores goes up because you need, more from the middle, or 1 from the side, in order to get those middle scores. Basically, once you start combining individuals and their scores, they're going to create those random combinations that lead to this normal curve. And that means that you don't have to know what your population distribution looks like in order to use that distribution of sample means. Because if this was our population distribution, nobody scored a 1 in our population, but twice as many people score a 5 as any other score, and everybody scores equally on 2, 3, 4, and 6. Let's say that that's our distribution for the population. Our distribution of sample means is going to look like that for a sample size of 1. It's going to look like that for a sample size of 2. That's a sample size of 3. That's a sample size of 4. That's a sample size of 5. So we can see that even here, with just 5 subjects, and nobody runs data with just 5 subjects. It's just hard to get to 30 when you're doing this on Excel. With just 5 subjects, it's already looking like a normal distribution. And it does not matter what your population distribution looks like. So it doesn't even matter if there's gaps in your population distribution. Nobody scored 1, nobody scores 4, nobody scores 6. Everybody scores either 2, 3, or 5. Well, that's your distribution of sample means for a sample size of 1. That's a sample size of 2. That's a sample size of 3. Sample size of 4. Sample size of 5. And you can see that even with this weird population, once we get to a sample size of 5, it's starting to take the shape of that normal curve. It's starting to have that bell shape. Very few individuals in the extreme, way more individuals in the center. And again, it's because these samples are combinations of people from the population. So the central limit theorem, again, importantly says that for any population, any distribution, any weirdly shaped population distribution, it's going to have a mean, it's going to have a standard deviation, and as your sample size, the distribution of sample means, let me get that second part in there. The distribution of sample means for a particular sample size will have a mean the same as the population mean. It'll have the standard deviation that is related to the standard deviation of the population. But importantly, it's going to approach that normal distribution as the size of your sample approaches infinity. So this is really what allows psychology to exist as a science, because we are dealing with individuals in a population all the time. And a lot of times we're dealing with very new populations that nobody has ever studied. So people might wonder, about the stresses and pressures that are being faced by single fathers, right? And they might say, well, I want to do some research on single fathers. What's the population of single fathers look like? What is the distribution of stress levels among single fathers? I have no idea. I don't know what it looks like. I don't know if it's a normal distribution. I don't know if it's flat across the top. I don't know if it's bimodal. I have no idea what the distribution of stress levels in single fathers looks like for the population. But as soon as you start taking samples, as soon as you interview 30 fathers and measure their stress levels, I guarantee you that the distribution of sample means of 30 fathers is going to be a normal curve. And that's what allows us to do the psychology research. Same-sex marriages didn't even exist decades ago, right? New population. If you're interested in doing research on same-sex marriages and what are the issues that they face, what are the challenges, that they face in their marriage, what are the differences between same-sex marriages and heterosexual marriages, you need to know what is the distribution. Well, no, you don't need to know what is the population distribution of same-sex marriages. And it's a relatively new population. So very little research has been done on it. I don't know what the distribution of the population looks like, but as soon as you start sampling, as soon as you find 50 couples, and that is your sample of 50 couples for your experiment, I guarantee that the distribution of sample means is a normal distribution. And that opens up Appendix 1 and all the tools of stats so that you can study this particular population. Millennials is another one that has recently had a lot of research done on it. And again, millennials didn't even exist prior to, what's the cutoff, 1995, I think, something like that. And, who knows what levels of depression are, what's the distribution for millennials? Who knows what IQ score distribution is for millennials? Who knows what tech use numbers are for millennials? I don't know what the distributions are, but I do know that as soon as you take a sample of millennials, the distribution of sample means is going to be normal. So this is something that is really beneficial, and really without it, psychology couldn't exist. I'll give you one last example. When I was doing my senior seminar, last time I did my senior seminar, one of my students, she came to me and she said, you know what, I want to do a study on a particular demographic that was identified by what is known as the Claritas prism. So this is a number of different demographics that the Nielsen company has put out that identifies different segments of our population. And she specifically wanted to focus on the group that was called connected bohemians. So she wanted to focus specifically on this population. And she wanted to say, I want to do connected bohemians. I didn't even know what connected bohemians were. So I read it, and it goes, these mix of young singles, couples, and families ranging from students to professionals, all have one thing in common, being tech savvy. They're always early adopters of the latest and greatest thing. That is what a connected bohemian is. She wanted to know about the color perception of connected bohemians. What is the population distribution for the ability to see, for example, red among connected bohemians? I have no idea whatsoever what that ability is, what that distribution is. But as soon as you get a sample of 15, 20, 30 connected bohemians, I know, because of the central limit theorem, that the distribution of sample means for those connected bohemians is going to be normal. And that's what allows us to do research on categories, populations, people that didn't even exist a few years ago. All right, so to wrap it up one more time, central limit theorem, any population opens up all of the world for psychology. It's going to have a mean, it's going to have a standard deviation, and we can figure out what that distribution of sample means is going to be from, it's going to have the same mean as the population mean, and it's going to have the same standard deviation. So it's going to have a standard deviation that's linked to the population standard deviation of the population divided by the square root of the size of the sample, and it's going to approach a normal distribution as n approaches infinity. So the central limit theorem allows us to figure out that distribution of sample means. That allows us to use the z-scores in the unit normal distribution table because other population distributions are not in there, but we know that our samples are going to have this particular distribution. So we'll wrap this up today with two mentions. So number one, we are now getting to the point where we have three separate distributions that we're going to be talking about on a regular basis. So I highly recommend that you get very clear on which distribution is which. So we have our population distribution. That is a distribution of individuals. So those are individual people with individual scores, and they're all living in individual apartment buildings. We have a sample distribution. And a sample distribution is when you take a sample from the population, and then these are individuals that have been taken from that population living in their individual apartment buildings in this sample distribution. So those we've seen previously. The new one today is when you take all of these samples and you take their sample means and you form a new distribution of sample means. And that new distribution is not individuals living in individual apartment buildings. It's samples living in individual apartment buildings. Everybody has roommates now, right? You got 5 people to each apartment complex. That's what a distribution of sample means is. And the great thing about the distribution of sample means is that the mean of the distribution of sample means, remember, we need to know what this is. The mean of the distribution of sample means is going to be the same as the population mean. And the standard deviation of the distribution of sample means is going to be equal to the standard deviation of the population divided by the square root of the size of the sample. So the first thing to do is to make sure that you're very clear when you're talking about population distribution, distribution of sample means, sample distribution. Be very clear about which one of those three distributions you're talking about or you're reading about. Try to keep them as separate in your mind as possible. The other thing that I'll just kind of foreshadow, you might be thinking to yourself, well, this is great because we wanted to figure out what the distribution of sample means is without taking a million samples. And we found out that the mean of the distribution of sample means is the same as the population mean. And the standard deviation of the distribution of sample means is related to the population's standard deviation. Well, that's all well and good, but we started off this whole exercise by saying that we don't know anything about the population, right? That's one of the challenges of doing psychology. So what good is the distribution of sample means that we can figure out based on information from the population going to be if we have no information about that population? Well, we are going to answer that. So put a pin in that. I don't want you worrying about that or getting confused about that. We're going to answer how we get around that little bit of an issue. But for right now, it's just important to understand the relation between the distribution of sample means and the population mean and what that distribution of sample means really is. Because again, it's the idea that you have a bunch of samples and their means all living in these little apartment buildings. That's what that distribution of sample means is. All right, any final questions or comments? All right, so we'll wrap up today. We got about half an hour. We'll devote that to practice time, homework time. So you got a homework assignment number 7 coming up. This is not due before next class. I just thought I'd put it on your guys' radar. It's chapter 4, part 2. Part of, I think what you need to know for it is, was taught today. So you can give that a shot, but it is due Wednesday, October 3rd by midnight. And I have been under the weather for the last about a week now. And if you've emailed me on Canvas Messenger, I will get back to you as soon as I can. And I will be updating the MyStatLab study points and any other corrections to grades that need to be done. So don't think that I forgot about it. I will be getting to it. So continue to try those pretest points. And remember that the deadline for 100% on any pretest is prior to the next exam that's coming up. So just kind of budget your time for those if you need to. Other than that, we got about half an hour for people to practice anything that they want to do or if they have any questions that they want to ask. But if you're a little bit feverish like me or if you you've had enough stats for the day, you can feel free to call it an early day. Otherwise, let me know if you need some assistance. Is that a question? Yeah. Okay. Why don't you come over here for a sec? All right, so we got an announcement from one of our students about a survey she's hoping some of you will complete.
Okay, I'm so sorry this is very last minute. I just need 5 individuals to fill out a survey for me for my non-experimental class. And it's about the treatment of gays, bisexuals, and lesbians.